So far we talked about movement of a particle on a line, and we derived all the equations for acceleration and velocity and displacement of that particle. Now we are going to extend that to movement of a particle in plane. So let's say we have a particle here which is moving around. And as we talked before about this, there are different ways to show the location of the particle in a plane. Probably the simplest one is just using xy coordinate or Cartesian coordinate. The location of the particle is going to be x and y. You can show it with these two variables. And when this particle moves around, this is the path of movement. If I know what is x and y at any time, I'm going to know the location of it and also velocity of the particle, and same thing for acceleration. So the location of the particle, if I show it with a vector like this r, this r can be written in terms of x and y. The location of the particle, which is r, is equal to x in the I direction plus y in the j direction. Now to find the velocity of the particle based on definition of the velocity, velocity is equal to derivative of position with respect to time. So I need to take a derivative of this equation, which is quite simple. Derivative of x is going to be dx dt times I hat. I hat is not going to change, right? So the derivative of it is equal to 0. And for the other terms, we are going to have dy dt in the j direction. Dx dt is going to be the velocity of the particle in the x direction. Dy dt is the velocity of the particle in the y direction. There are some conventions about derivatives. Usually people show derivative with respect to time with a dot. So x dot means derivative of x with respect to time. Same thing for y. dy dt, we can show it with y dot too. And again, this x dot is the velocity in the x direction. And same thing for the y direction. dy dt, we can show it with y dot. Or the velocity in the y direction, which I show it with v index y. So this is velocity in x direction. And same thing for y. If I take another derivative from this equation, I'm going to be able to find acceleration of that particle. Acceleration, in general, it's equal to derivative of velocity with respect to time. So it's going to be second derivative of x with respect to time times I hat. Second derivative, we can show it with double dot. So x double dot means d squared x over dt squared in I hat direction plus y double dot in j direction. So these are the equations for movement of a particle in plane using xy coordinate. Sometimes we know the acceleration, for example. We know the acceleration is 0 in the x direction. Then you can use all the equations that we had for movement in the x direction independently for x direction and y direction. So what's the meaning of that? I'm going to show that with an example, which we are going to have a lot of questions about this category of problem. Let's analyze projectile motion. So let's say we have a particle which we gave it an initial velocity. We shoot it from this initial position. Let's say the coordinate of this point is x0, y0, the initial point. And the direction of the initial velocity is theta from the x-axis. Let's say we have gravitational force here. So this is a projectile motion. We are giving an initial velocity to it, so it's going to go up but gradually it's going to come down because of gravitational acceleration, right? Now, how we can analyze this movement? By analyzing, I mean how we can find the position, velocity, acceleration at any time. Okay, so we start with acceleration. Because if we consider the friction force, the drag force from the air is negligible, when this particle is moving on this trajectory, there is no force in the x direction. And because there is no force in x direction based on Newton's equation, there is not going to be any acceleration in the x direction. So for projectile motion, x double dot, or we can show it with ax. Ax means acceleration in the x direction, or x double dot, is equal to 0. And for the y direction, we always have gravitational acceleration downward. So acceleration in the y direction, or y double dot, is going to be equal to, because it is downward, it's going to be negative g. So acceleration in the x direction is 0, because there is no drag of the air, there is no force. And acceleration in the y direction due to gravitational force is going to be negative g all the time for a projectile motion. So we have constant acceleration for the x direction and constant acceleration for the y direction. So I'm allowed to use all the constant acceleration equations that we had before for the x direction and for the y direction separately. What's the meaning of that? For the velocity in the x direction, for example, velocity in the x direction, or x dot if you want to show it, based on those equations that we had in previous video, it's going to be equal to the initial velocity in the x direction. So let's write it v naught in the x direction. This means initial velocity in the x direction plus acceleration in the x direction times t. We had this equation for movement of a particle on a line, right? I'm using exactly the same thing. So velocity in the x direction at the beginning is going to be v0 times cosine of theta. That's the initial velocity. So v naught in the x direction is equal to v0 times cosine of theta. And acceleration in the x direction is equal to 0. So the velocity in the x direction, or x dot, is going to be v0 initial velocity times cosine of theta all the time. So at any time during this movement, velocity of the particle in the x direction is going to be v0 cosine of theta. And we can do the same thing for y direction. Vy, or y dot, is going to be equal to, based on the equations that we had in previous section, it's going to be velocity, initial velocity in the y direction, plus acceleration in the y direction times t. Initial velocity in the y direction is v0 sine of theta. And acceleration in the y direction is negative g. So it's going to be v0 sine of theta minus g times t. So if you know what is the time, at any moment you can find the velocity in the y direction using this equation. Okay? For example, if you want to find at what time this particle goes to this top point, so at this top point, velocity in the y direction is equal to 0. You can put this equation equal to 0, and from there you can find time. So t for this top point is going to be v0 sine of theta divided by g. Okay, and you can do the same thing for displacement. Again, because accelerations are constant in both directions, I'm allowed to use those algebraic equations for displacement. So position is going to be equal to initial position plus initial velocity times t in the x direction. Initial velocity in the x direction is v0 sine of theta times t plus 1/2 of acceleration in the x direction times t squared. And acceleration in the x direction is equal to 0. So using this equation, I'm going to be able to find the location, the x location of this projectile at any moment using x naught and v0 and time. And we can do the same thing for y direction. The y of this projectile is gonna be initial point of it in the y direction, or y naught, plus initial velocity in the y direction, which is v0 sine of theta. Okay, I found a mistake here. Initial velocity in the x direction is v0 times cosine of theta. Sorry about that. So let's go back to this equation. Y is going to be initial position in the y direction plus initial velocity in the y direction times t, plus 1/2 of acceleration in the y direction times t squared. Acceleration in the y direction is negative g, so I'm going to have minus 1/2 of g times t squared. Okay, so using these two equations, I can find the location of this particle, this projectile, at any given time. And we also had time-independent equation too, right? The time-independent equation, because the acceleration again is constant in both directions, we can use that equation independently for x direction and also for y direction. So based on that equation, 2 times acceleration in the x direction, let me write that equation here, 2 times acceleration times displacement is equal to velocity squared minus initial velocity squared, right? So this is the general equation. Now if I want to write it for x direction, 2 times acceleration in the x direction, which is 0, times displacement, so 0 times anything is going to be 0. Velocity at any time is squared minus initial velocity in the x direction is squared is going to be equal to 0, which means velocity is not going to change, which we had it here too, right? Here we showed velocity in the x direction is not going to change. So that's not going to be really useful for x direction. For y direction, we are going to have 2 times a in the y direction, which is negative g. So I'm going to have negative 2 times g times displacement in the y direction is equal to velocity in the y direction is squared, which is this one, or in general vy squared, minus initial velocity in the y direction is squared, and initial velocity in the y direction is v0 times sine of theta squared, which is the time-independent equation in the y direction. The time-independent equation in the x direction, as I showed you, is not going to give you anything new. It's just going to show velocity in the x direction is not going to change. Okay. This is the theory for this part. I'm going to show you how you can use these equations in solving problems.